nanohub.org.
Online simulation and more for nanotechnology.
All right, so today we'll go very quickly again over what we talked about last time, basically supervised learning and regression. I'm going to remind you about least squares and the likelihood approximation, and then we'll start addressing one by one the problems that we identified, and I'll go over them again. We'll introduce the maximum posterior estimate, which is a very simple generalization of the maximum likelihood that kind of works, but if you really think about it, it gives results that are garbage, and I'll explain why, and why you should not really use it. Bayesian, then we'll talk about Bayesian linear regression, which is basically the right way of doing inference in these problems, but we'll still need a way to say something about the hyperparameters of our model, like the length scale or the width of the radial basis functions, or which basis functions you should use, and so on and so forth, or even the noise. Okay, so you're gonna have to make a decision about what the noise is or what all the other parameters are, except the weight. And to do that, we'll see that, you know, being fully Bayesian, it's a little bit difficult because we don't know yet about Markov chain Monte Carlo. We'll learn about it later. So we're going to have to come up with an approximation to being fully Bayesian, and that approximation is going to be called the evidence approximation. It's the first order approximation to being Bayesian. And then we'll talk about a specific hierarchical Bayesian model called automatic relevance determination that will give us the ability to automatically decide which basis functions to include in regression. And again, we're going to see it through a very specific one-dimensional regression example, but all of these things are generalizable. Okay, so we talked about supervised learning last time. Supervised refers to the fact that you have both inputs and outputs, and you're trying to find the map between the inputs and the outputs. If you didn't have any outputs and you just had to learn something about the inputs, that would be called unsupervised learning. Now, regression is a specific case of supervised learning in which the outputs are scalars or they're continuous variables. If they were discrete variables, we would call the problem a classification problem. Now, a generic regression model has this form, and you're looking for these parameters, W, okay? And this form right here could be a nonlinear model, and in real life, that model could be your physical model, and that W could be some parameters that you need to calibrate, okay? But this is the simplest possible model. You could have a linear model. This is not necessarily a good model because it is very unlikely that it's going to satisfy any of the physics of the problem, okay? And you can go a step further and go to, instead of expanding something in a linear basis, expand it in a nonlinear basis, and these guys here, the phees or the basis functions, we call them the features, okay? And if you choose the features correctly, if you choose them to satisfy certain invariances that are satisfied by your physical problem, then the final model will satisfy the same invariances. Questions? And we saw that this is really your choice. It could be anything you want, okay? So it could be, if x is like a vector, it could be monomials made out of that vector. If x is a scalar, you could make these sines or cosines. You could make them radial basis functions, these belts. You could make them step functions. But it could go even further than that. X could be, for example, a picture, okay? And the phi could be a feature of that picture, Like you look, for example, at, I don't know, how much of a specific color you're getting, right? Or whatever, basically. Any feature that you can define in that picture. Or it could be also an audio file. And it could be a feature of that audio file. Like how much, so let's say, amplitude you have in a specific bandwidth, whatever, okay? It depends really on your problem. But thinking like that, thinking in terms of generalized linear models, you can do regression between an X that is basically anything, from a vector to a picture to audio to text to whatever, okay? So X could be whatever as soon as you can turn it into features that are numbers, okay? And then you can try to connect that X to whatever your Y is. Make sense? It's not that trivial, obviously, to create features for pictures or audio or whatever, but as soon as you can do that, then everything else that we're talking about works in exactly the same way. Okay? Questions? All right. And we discussed about least squares. This is the simplest method to train the model, these kinds of models, generalized linear models. You basically define a loss function by squaring the errors of your model and summing them up. Okay? And we said that this has an analytical solution, almost analytical. You need to do a little bit of linear algebra. But it suffers from many problems. For example, it doesn't give you a way to quantify the measurement noise. It doesn't tell you how to choose base functions and which. Yes?
You said it was the simplest way to train the model.
To find the best weights, so the best parameters of your model. So by train, okay, that's a very good point. I need to explain the terminology. So I'm going to be using in exactly the same way the following words. Train a model, fit a model, learn the parameters of a model, calibrate a model. All these are synonyms. Any other way of saying the same thing? I don't know. Okay, so train, fit, learn, calibrate, same thing. Okay? It's all finding the best parameters. And the best, of course, is it's subjective, and we're going to be discussing it. Anyway, so which and how many base functions do we use? We cannot really answer it with least squares. If there are parameters in these basis functions, like the widths of the radial basis functions, for example, then it doesn't give us a way to pick them. And it doesn't also quantify the epistemic uncertainty induced by the limited data set. So you can imagine that if you're training your model using 10 observations, you're going to be more uncertain than if you use the 100 observations. So least squares cannot really quantify that uncertainty. Okay, it's not anywhere to be seen. Any questions? All right. So the first version of the first extension that we saw was basically the maximum likelihood extension. We got rid of the loss function, we got rid of the square loss function, and we introduced an explicit model for the measurement process. Right? So we said that we're now going to not only say something about the map between X and Y, that is the physics, for example, but we're also going to say something about the measurement. Okay? And we said this about the measurement. So we said that we have a model that tells us how likely it is to observe these Y's at these X's if the physical model had these parameters. And of course, we introduce a Gaussian measurement model because that's the easiest. But this is not necessary. This is not restrictive. You could make it anything that corresponds to the actual measurement process. But for the Gaussian, which is the easiest to use and leads to nice analytic results, then you read this as follows. The probability that you observe a specific y at that x given all the parameters of the model is Gaussian, okay, centered around the model. So the mean prediction, the mean guess, if you like, is the response of the model, plus some noise with a variance sigma square that corresponds to random stuff kicking around the response. Okay? That's the idea. Now, I'm 100% sure that if I ask you, what does this mean? Only Sarmila knows, because only Sarmila asked me last time what it is. So I'm gonna tell you now what it is, okay? What this notation is. I forgot to tell you what this notation is. So I will tell you right now. So this thing is the PDF, the probability density function of a normal with this mean and that variance evaluated at that point. Okay? So let me write it down again. So when I write n, let's put here a z, mu sigma square. What I mean by that is the PDF of a standard normal with this mean and that variance evaluated at z. So that will be 1 over square root 2 pi sigma exp minus mu minus z squared 2 sigma squared. That's what it means, okay? It just is that quantity, all right? And I'm gonna be using this notation liberally to write other stuff later on. For example, I may write EZR to talk about the PDF of an exponential with that rate parameter, which would be, now I don't remember it exactly, but it's probably this, okay? But these are going to be specific functions. Make sense? Any question? Yes.
I don't understand what evaluating that yi means with respect to the models that we're calibrating.
So this quantity here gives you the probability that you observe y when you measure at x. So all that this is saying is that this probability is a probability that you would get if y was a Gaussian with this mean and that variance. So it's a statement basically that this quantity is 1 over square root 2 pi sigma exp minus yi minus yxiw squared 2 sigma squared. That's it. It's as simple as, I could be saying this. I could be just writing this thing down. But it's just too much. Okay? Yes. This? Oh, this is another example. Forget about it. Forget about it. Okay? It's another example of writing the distribution of an exponential. But today I will basically just be writing the normal. Okay? This is very good because guess what you're going to see in your homework? You're going to see exactly that. Okay? You're going to practice a little bit with this concept. All right. So when we said that we're going to be maximizing the likelihood to find all the parameters, including the weights and the variance. And and with that we were able to estimate the noise level. And using this information, we can come up with error bars, lower bound and upper bound for our prediction. And we can use the mean as a median prediction, if you like. And this is pretty much it. Okay, but still, the only thing that the maximum likelihood approach achieved was to give us an estimate of the noise. All the other problems remain there. Okay? So now we're going to start addressing these problems one by one. So the first thing we're going to do is talk about the maximum posterior estimate, which is the first step towards being Bayesian. And let's just do it. All right. So as before, we have this model, which is a generalized linear model. Okay. As before, we have an explicit model for the measurement process called the likelihood model. Okay. And that is going to be a Gaussian also, or just like before. But now here's the new thing. The new thing is this. We now go to the weights and we say the weights are a parameter that we're looking for. Therefore, we are uncertain about it. And what have we learned? We have learned that everything, if we have something about which we're uncertain, we better use probability theory to talk about it. Okay? So what we do is we say we have that W, we don't know what the W is, let's just put a distribution of that W. If we don't know anything about that W, well, you better put a distribution that is very, very broad. Okay? Flat, for example. You can put a flat one. Okay? But you can also put something that is less flat. But anyway, in any case, you add this ingredient, a prior on the parameters of the model. So let's see what we have so far. We have a model. We have, which is a model of the physics, right? Or a physical process. We have a model of the measurement process, which we call likelihood. Okay? And then we are basically saying something about all the parameters of our model. Okay? We are forced to say something about all the parameters of our model before we see any of the data. Okay? You don't know what to say? Go back to lectures and use the principle of indifference, use the principle of maximum entropy to say something. Okay? Any questions? All right. So here's one choice as a prior for the parameters of the model. This is the simplest possible choice. Okay? And it's not by any means the best choice, but it's a choice. You pick the prior of the weights to be Gaussian. With the parameter alpha, that parameter alpha here controls the precision of that Gaussian. It's the inverse of the variance. The bigger that alpha is, the more concentrated your prior is around zero. The smaller you make that alpha, the broader you're making it. Alright, so for example, if we had a one-dimensional weight, and 0 was here, a big alpha will give us something like that. So let's say that would be alpha equals 0.01, and a small alpha, a big alpha will give us something like that. Alpha equals, let's say, 10, whatever. Okay, so that alpha controls your prior uncertainty about the weights. And of course, if you are very uncertain about the weights, make that alpha very, very small, and the distribution will become flat. Okay? Any questions about this? But this is just a choice, okay? Just the model of my state of knowledge about that W before I start seeing data. Anyway, a name for that alpha is precision. And this is the interpretation. Before we see the data, we believe that the weights are around 0 with that given precision. That's what this statement means. This may be true for whatever I'm doing right now. It may not be true for your problems, but it's a starting point if you have absolutely no idea about what that W is. Okay? Questions? Alright, so now we have model, likelihood, prior. And there's only one thing that we can use, and that is the product rule. I mean, we can use two things. We can use the product rule of probability theory and the sum rule of probability theory, and that's pretty much it. There are no other principle that we can use. Okay? So what we do now is we use just Bayes' rule, basically. Okay? So let's see. Let's read what we have here. We're asking the question, what should I think about the weights after I see the data? That's the question I'm asking, right? So I'm asking the question, what should I think about the weights after I see some data? So I'm conditioning on the data. So you remember that we said probability of A conditional on B is the product of A and B, right? Divided by the probability of A. This Bayes rule. It's the same thing, only now A is the W takes these values, and B is I have observed this data set. Okay? It's the same thing. And so let's actually write it here so that you can see it, right? A, B, and here you have B given A times the probability of A, and then you have a normalization constant. Okay, so this is the product rule. Remember the product rule? PA given B is going to be PB given A times PA. It's the product rule. Okay? So this is red. That probability is proportional to your likelihood times your prior. Okay? And this guy right here is just a constant that's going to make this thing prior times likelihood is going to make it integrate to 1. On the left-hand side, you have what we call the posterior. I'll explain this. I'll talk about this like 1,000 times. Okay, but here's the whole picture. So you're saying, let me see some data. What is the right way to update my state of knowledge about the weights of my model? And you say, okay, here are my weights. Let me just condition on the data I see using Bayes rule. And when you use Bayes rule the right way, when you condition, you're going to get likelihood times prior. That's what you're getting. So you're going to get something proportional to likelihood times prior. We're going to put this as an exercise, okay? But you are going to have to internalize this, which is one way to write the product rule, okay? But anyway, we remember the following thing, take home message. To update your state of knowledge about the weights, you take the likelihood and you multiply with the prior, and that's going to give you something that's proportional to your posterior. So the whole training, let's say, of the model becomes a question of characterizing this quantity. How do you characterize this quantity? Can you calculate it analytically? Is it a known distribution, or is it something more complicated? Any questions? So the right Bayesian step will be to fully keep this distribution as is and see where it takes you. But you can make a crude approximation. You can say, well, I'm just going to maximize the posterior with respect to the weights. So I'm going to pick the weights about which I am more, that I think are more probable after I see the data. Okay? So let's do this. So instead of the likelihood, you maximize the posterior. Now you maximize something that is proportional to your posterior. Your posterior is this divided by a constant. Okay? But it's the likelihood times that prior. Okay, so it's exactly the same as your maximum likelihood, but it has this additional factor in there that affects things a little bit. Now, if you work with a logarithm and your prior is Gaussian and your model is linear and your likelihood is also Gaussian, then that posterior will be proportional. The logarithm will be this expression plus some constant that doesn't depend on the weights. Okay? And you see that it looks pretty much like your maximum likelihood. Okay? So this is basically comes from your likelihood, but there is an additional term that comes from the weights. Okay? So you have the term that comes from the likelihood and the term that comes from the weights. So if you make alpha equal to 0 corresponding to a completely flat prior, you get maximum likelihood. Okay, now you see how everything is connected. if you are Bayesian and you start with a flat prior and you're maximizing the posterior, let's say, you get maximum likelihood. If you're using maximum likelihood with a Gaussian likelihood, you're basically doing least squares. So everything is connected and everything is consistent with each other. I mean, one thing is a generalization of another. But anyway, so this is the problem you need to solve now. And of course, as before, you take the derivative with respect to w, set it equal to 0, and you solve for w. And you're going to get this solution, which differs from the least square solution. The least square solution doesn't have this in here. And this doesn't appear in there. Okay? So it has this term. And what this thing does, what this alpha does, it is actually regularizing your solution. It penalizes very big weights. So the weights you see, they appear here, and that alpha, if it is big enough, it will not allow W to become too big. This is what happens. So it keeps W down so that you don't overfit. But of course the question is, what is that alpha? Because I haven't told you that. How do you find that alpha? Okay? But if you fit, let's say, the same data with alpha that gets progressively bigger, you will see smoother and smoother results. And one of these alphas is the magic number. Okay? That you need to figure out in another way. But anyway, how would you solve this problem? This is a linear problem, okay, that you need to solve, linear system. And you cannot use QR like we did before. You need to use the Cholesky decomposition. You get a homework for that. Don't worry about it, okay? But a stable way to solve the problem is using the Cholesky decomposition, blah, blah, blah. Okay. So unfortunately, so let's talk about finding alpha and sigma. So you can try to find alpha and sigma by maximizing the posterior, but this is not the right thing to do, and you will probably overfit if you do that. So you need something else, and we'll talk about it in a while. Okay. The right thing to do would be to put a prior on alpha and sigma and write down their posterior. That's the right thing to do. Anyway, you can extract lower and upper bounds from the maximum posteriori estimate of the parameters. And in any case, that's how it would look like. And it will be a little bit more regularized than before. Okay, so you include the alpha that is a little bit big, and things will start to become smoother. If for very big alphas, you will underfit. For very small alphas, you will overfit. There's a magic alpha that will just be right, but we haven't said how you can find it. Okay. That said, this pretty much concludes. I mean, this is the effect of no alpha and alpha, right? So including that alpha, including a prior on the weights, will make things smoother. That said, you should probably not use the maximum posterior estimate ever. Okay? And yeah, apart from the fact that it's basically as good, it's actually not even as good as maximum likelihood. And I will tell you why. But it doesn't address any of these issues. Yeah. So it doesn't tell you how to pick your basic functions, which one to pick. It doesn't even tell you how to pick that alpha that it introduced, right? It doesn't quantify epistemic uncertainty induced by limited data. And it's, in addition to all this, it's also a bad approximation because of a very strange thing. If you, instead of the weights, you decide to work with a function of the weights. So you say, well, instead of maximizing, let's say, W, I'm going to be maximizing W to the cube. You will get a different answer. which is ridiculous, okay? You would just get, I mean, it doesn't make sense. So the maximum likelihood doesn't have that problem. Neither does the fully Bayesian approach. Okay, so if you want, the maximum posterior estimate is not invariant with respect to how you look at your problem, and that's always not a good way to look at your problem. All right, but it's something that people do all the time. That's why I felt obliged to talk about it. Okay. All right, probabilistic regression version 3, Bayesian linear regression. This is what you should do. Okay. And for a generalized linear model with Gaussian likelihood, there's absolutely no reason why you should not do it, because everything works out smoothly and analytically and really, really, really nicely. Okay? So one more chance to repeat what we said 10 minutes ago. You have your model. You have a model of the measurement process, which we call likelihood, and somebody forces you to say something about the weights of the model before you see any data. You are picking a prior. Okay? So model, likelihood, prior. And then you put everything together to come up with a posterior state of knowledge about the weights, posterior in the sense that it is after you have seen some data, and that posterior is always going to be proportional to the likelihood times the prior, and this is just an application of the Bayes rule and nothing else. And that thing right here, normalization constant, is completely irrelevant for the time being. It will be useful later to do something. Okay. But anyway, this is pretty much it. So now instead of saying, well, this is too much, let me just maximize this, we're just gonna keep the whole thing. Okay? And what we're gonna see is that if this is Gaussian and this is Gaussian, then this is going to be Gaussian. Okay? And this is a common thing with the Gaussians. Gaussian times Gaussian is a Gaussian. Gaussian, you integrate over it, you get a Gaussian. Okay? And that's why we use them all the time, because they're very convenient. Okay? And if they happen to be the right model, then everything is nice. Okay? All right. So, let's see. If everything is Gaussian, you will get a Gaussian. Okay? For the posterior of the weights. Sure. So you started with your prior state of knowledge being a Gaussian. You condition on the weights, you condition on the data, and you get another Gaussian. Okay? The Gaussian you started with, this guy up there, was a zero mean Gaussian with a very, very, very large variance. Okay, very, very flat Gaussian. And now it became a Gaussian that has a mean and some covariance matrix. Okay, now this quantity right here is the PDF, the probability density function of a multivariate Gaussian. What we saw before was the PDF of a univariate Gaussian. This is the PDF of a multivariate Gaussian. This W does not get, it's not a scalar, it's a vector. Okay? So if you wanted a formula for that, this formula will probably because I don't really remember it, but it would be kind of like that. Determinant of this minus 1/2, exponential minus 1/2, W minus mu, T, S minus 1, W minus M. It will be this formula. Okay, so you have this normalization constant, determinant of the covariance matrix, exponential of this expression right there that is W minus mu, transpose, inverse of your covariance, whatever. Okay, so we'll talk about the multivariate Gaussian in detail later. Next Tuesday, actually. Okay? So don't worry too much about it. You'll get a homework problem on it. But anyway, it's a generalization of the univariate Gaussian. Let's just say that. Now the mean and the covariance are given by these expressions. So you see that the covariance kind of looks like we were getting, we're maximizing the likelihood, we're getting this matrix somewhere in there, exactly this matrix, and the mean is this. Okay? So actually, if you look carefully, you will see that the mean is the same as the one you would get by maximizing the posterior. It's the same. It's the weights you would get by maximizing the posterior is the mean. Okay, if you made alpha 0, that would be the least squares estimate. But in addition to that, you get this covariance matrix that captures the epistemic uncertainty about the weights. This is the extra thing you're getting. Okay? And now what's going to happen is that this covariance matrix is going to disappear somehow if you add enough data. Okay, if you add enough data, it will say, you know what, I'm just gone. Okay? But let's see, okay, so this is the definition of the multivariate Gaussian. Have included it there for your education, but we'll talk about this for almost half a lecture, so I'll just show you how it looks like. And I'm quite sure that everybody understands how it looks like, okay? Corresponds to a random variable that is concentrated around that M, and that covariance matrix S describes how much uncertainty there is around that M, okay? And that could be uncertainty in terms of a blob like that, but the blob could also be an ellipsoid, and so on and so forth, okay? Anyway, and again, you need to do the computations in a stable way, and the way you do it is by the Cholesky decomposition, and you'll get the chance to play with that. Okay? Okay, so this is the posterior of our weights. It turned out to be Gaussian, and now we are in a position to start making predictions. And this is something that, I mean, it's actually trivial. Unless you look at, I mean, if you start from that formula, it doesn't look that trivial, but it is actually very easy to do. Okay? So here's how we go. Here's how we think about it. This is the measurement model, right? So this right here is the measurement model. It's the model that tells us what we should expect to see at X if we measured at X, and the model parameters were these, right? You remember? This is our likelihood. What am I going to see at X if I measure Y? And I know the parameters of our model. So this is this nice Gaussian that we introduced to model the measurement process. And then we're saying, okay, this is what we would see, but we don't really know what the W is. So let us multiply with our posterior probability of what W is. So we say, okay, that's what we would get if we knew W, but we don't know W, and that's the best thing we can say about W. It's the posterior. The posterior is what the best thing we can say about W. So you just put it in there, okay? You weight with the posterior. But then you say, well, I don't really know what that W is, so let me just integrate over it. Does that make sense? So that's one way to see it. Okay, to say, here's my measurement process, which is conditional on the parameters, and that's the best thing I can say about the parameters, but let's integrate them over because I don't really know them. Okay? So that's one way to think about it. The other way to think about it is to start here and say, guys, I want to say what is the measurement I'm going to get at X if I measure Y. So what I'm going to get at X if I measure Y, and if I take into account all the data I've seen. Okay? So what will I measure at X if I take into account all the data I have seen? And then you use the sum rule of probability theory. So from here, you go and you use, here you can go directly to the sum rule, which is, well, tell me what you're going to see if we also introduce that weight in there. Okay? So this is like an identity. You just introduced one more variable and you integrate over it. Okay? So you're gonna get whatever you started with. But here now you can apply Bayes' rule and you will get here. Okay? Let me remind you what this rule was. It was the following rule. The probability of A is sum I and the probability of A conditional BI times the probability of BI. That's exactly what you see here. Okay? It's exactly this rule. So if there is one take-home message, there's more than one take-home message. So the take-home message number 2, okay, is how do I make predictions? And really, to make predictions, all you need to say is, oh, let me make the best prediction given the data I've seen, and then use the 2 rules of probability theory. It takes a little bit of practice, okay? So you need to do it for like a year, and then you'll get it, okay? But it is a starting point. All right. Now, we are lucky because this is Gaussian, and this is Gaussian, and Gaussian times Gaussian, it's a Gaussian integral over something that's going to give us a Gaussian, okay? So, you will get a Gaussian for the predictive distribution. So the predictive distribution there, you can do all that analytically. I'll give you a homework to do that exactly. And you will get a Gaussian. And that mean and that variance, they're going to be like that. So the mean is going to be this quantity right here. The variance is going to be this quantity. Okay? Mean and variance. And you see that the mean is the mean of the weights times the basis functions. So this is basically your model, right? With the weights being the mean. But you have this additional term that is a little bit strange. Before, when we were doing maximum likelihood, we just had this term. Now we also have this. This is, oh, I can actually do this. This is great. So we now have this term, which is which we didn't have before. Okay, so this is the posterior mean prediction. This is how we're going to call it. And then this is the posterior variance, or the posterior predictive variance. And this term right here is the noise. It's our estimate of how much of our uncertainty is due to noise. And this term right here is a new term. And it's the epistemic uncertainty induced by the limited number of observations. So the more observations you add, this will go away, but this will stay. The noise will stay, this uncertainty will disappear. Okay? And of course, if you make this disappear, there's no point to make any more measurements because you cannot really reduce this term. Question?
So the epistemic uncertainty constant that we have, does it try to make our model much better?
So this does not make your model better. This tells you how bad your model is. Okay? This is the difference. So what we didn't have before with the maximum likelihood of the least squares was exactly this term. And a quantification of how uncertain we should be about the weights that we have found, about our predictions. Okay? How uncertain, not because of the measurement noise, which is there anyway, but because we don't have enough measurements to even say what is the mean of the underlying, you know, the true model that generates the data before they get contaminated by noise. Yes?
What about alpha? Because in the...
It's hidden inside here. It's hidden inside here, inside there. All these are dependent on alpha.
So, previously you showed something similar in a few slides back. What was the difference between those two? Because you showed a mean again.
Yeah, before I talked about this thing right here, right? Which was the posterior of the weights. So this was the posterior of the weights, and it was given as a multivariate Gaussian with a mean and the variance that I said you calculate like that, right? But now this is, now I'm using this result to make predictions. So this is the best you can say about the parameters of your model, okay? And you say that my parameters are like that. Now I'm taking this information and I am propagating it through the measurement process to say something about what I'm gonna measure if my parameters are like that. So this is what you see here. You see the uncertainty of the parameters going through the measurement process and being put together, let's say, in a way, so that you can come up with a distribution for what you will measure. Okay, but again, the take-home message is that your prediction will contain two sources of uncertainty, noise and this thing which is epistemic. Yes?
What's little s squared?
The last word, epistemic,
S squared of x is the line above in the normal distribution.
S squared, yeah. Predictive variance, the whole thing.
In the line above. In the line? Yeah. S squared.
S square, yes. What is the question?
Just what's that term?
This term? This term is the predictive variance. Okay, so let's, it probably makes sense to talk about it in a little bit more detail. All right, guys, here we go. Give it 1 second. All right. So here's what we're gonna do. We are asking this question. We're saying, as I write, listen to what I'm saying. What should I say about the y I measure at x if what I have seen is this data set? Some measurements of x's and some measurements of corresponding n's. All right, so do we all agree that this is what I'm saying? I'm asking the question, what will I measure at y if, I try to measure y at x, taking into account all the data I've seen, okay? So this thing here is called the predictive density, okay? So this is my prediction. My prediction is as simple as saying, I'll tell you what I think about y conditioned on all the data I've seen. That's all, okay? And then this thing here, you need to somehow resolve it into the things that you have actually, the constituent parts of putting together your model. So you're saying, I cannot really say what this thing is like that. I need to introduce other things. So, and you notice that if you introduce that W, why do you start that there? Because you already know the answer is the answer, but let's just observe that this holds just like that, okay? So what did I do here? I introduced this W next to my Y. So now I'm asking the question, what do I think about Y and what do I think about W given all the data I've seen, okay? This is what I'm asking here. But as soon as I'm integrating, if I integrate this expression over W, so if I take what I think about Y and what I think about W, and I integrate out of the picture W, I'm gonna get what I think about Y. Make sense? So now I have this. And now in here, I need to make appear whatever I already know. Okay? So here I will introduce the likelihood and the posterior of the weights. So if you use Bayes' rule for this term right here, you're gonna get PYW. Actually, let's write it like that. PYXW times PW X1N Y1N. This also holds because you can easily decompose this distribution like that, right? Because if you want to say something about Y, it suffices to know W to say something about Y, because Y controls your model. So this is absolutely valid, and it's your likelihood process. And then there only remains W to be conditioned with whatever you had before. Okay? And then it turns out that this thing is actually a Gaussian. with a mean and a variance that is like that. How do I know? We'll make it a homework problem. That's how I know. And it is this, 1 over square root 2 pi Sx. It is an expression that gives you the probability of observing y at x. It is this. Okay? So I'll try to motivate this through a homework problem. Why from there you get here? This is just algebra. This step going from this integral to this normal. It's algebra, and this is just the definition. So to answer your question in like 10 minutes, this is the predictive variance. This is what this thing is. So it is how uncertain you are about the measurement of y after you see the data. This is what it is. Now, why it is what it is, you're gonna have to derive it and see it. Okay? Does that kind of answer your question? I mean, you have to say yes. Anyway, let me just show you how this thing looks like, okay? And perhaps, you know, this will highlight a few things. So here in this plot, I've put both uncertainties. So the green uncertainty is the total uncertainty we have, everything, S of x, all of it. And then the red one is just the epistemic uncertainty. Okay? So the red thing, it's actually pink. The pink one is epistemic. It's our uncertainty because of the limited amount of data that we have. It's our uncertainty about the exact location of the green curve. Okay? It's this kind of uncertainty. But the green one is our total uncertainty. It's uncertainty about the location of the green curve and uncertainty because there is some kind of noise added to whatever we measure. Okay? So the red is the epistemic uncertainty, and the difference between the red and the green is pure aleatory uncertainty. Okay, yes. When I'm saying noise, I'm talking about variation that is not due to X. Variation in your measurement process that is because of other things that you can't control. Yes?
So if you added more data points to that graph, then the red line should get smaller.
The red line, if I added more points, the red line will disappear, and the green shaded area will stay there. That's what will happen. And if you are collecting data, let's say, for fitting a model, and you can visualize these two kinds of uncertainties, it only makes sense to collect more data if you still have some red left. If your red has disappeared, you cannot really learn anything more. You have nailed it. Okay? Anyway, let's say that we just wanted to get our epistemic uncertainty. To get just the epistemic uncertainty, we need to take the complete uncertainty and subtract from it the noise uncertainty. So the difference between the complete uncertainty and the noise is basically just the epistemic uncertainty. And now if you wanted all the uncertainty, we just use the full thing. Okay? So if you go plus or minus 2 times just the epistemic uncertainty, you will get the red line, plus or minus 2 times the full uncertainty, you would get the green shaded area. It's a quantile. So my prediction is a distribution, and I'm asking for a lower bound and an upper bound so that I can bound y with 95% probability. I'll put that on the homework as well. So every time you ask something, it goes on the homework. That's seriously. I think that this is a great idea. So if you don't ask anything, I'll just make it up. All right. So let's do something else that we could not really do with the maximum likelihood. Okay. So what I'm going to do now is I'm going to explicitly use the posterior of the weights to sample plausible models. Okay. So this is something that you probably haven't seen before. So this distribution is our state of knowledge about the parameters of our model. So what I'm going to be doing now is I'm going to sample from this distribution, and each sample would correspond to a model that is good. Good in the sense that it could be the right model. If you sample again, you'll get another model that could be the right model, and you just can't decide which one is the best, okay, yet. So, but let's see how it's going to be like. So these red lines that you see here are plausible models, are basically 5 plausible models. How do I get them? I sample a W for the posterior of the weights, and then I plug it into my functional form for the model, and then I just plot that model as a function of X. And then I sample another W, and I plot that model again. So the other model again. So let me just show you. You take a W, let's say WI, you sample it from the posterior. Okay, the posterior is this, let's say. This is Gaussian, so you can just get a nice sample easily. And then you take this W that you have sampled, and you put it in your model. Okay, and you plot X, X as Y as a function of X with that W in there. Okay, and each red line corresponds to a different W. So if I ask you which one of these models is the right model, what you should say is, I don't really know, they all look good to me. Okay? And now you will see where the epistemic uncertainty comes from. This is pure epistemic uncertainty. Question?
When we are sampling Wi, that means we are sampling W1, W2, W3, right?
Yes, you're sampling all the weights of your model. So let's...
I'm just changing all the weights, not just one.
Yeah, all of them. You sample all the parameters of your model from the posterior distribution. Now here's what you will see if you sample 10. Okay, and you will see basically the epistemic uncertainty bounds appearing here. If I sample 100 times, 95% of these lines will be within the bounds I drew before. Okay, but again, these are 10 models. Which one is the right one? I don't really know. Okay, you cannot really select one of them. I mean that any of these models is as good as any other.
Why are there so many models?
Because you are uncertain about the parameters of the models. So, okay. If you don't have somebody forcing you to pick a model, you should not pick a model. Okay? So unless somebody's putting a gun in your head telling you pick a model, then you would pick a model, okay? And then we would have to come up with a way to pick a single model. But as soon as somebody doesn't do that, then when you use all your data, you cannot pick one model because there's not a single model that appears to be the best. There are lots of models that are compatible with the data and with your prior assumptions, and each one of them is as good as any other. And the only solution out of it is to collect more data. And when you collect more data, what is going to happen is that these will collapse to a single model. But you need more data for this to happen. Does that make sense?
Where is each line from?
Where is what?
Each line, red line, red curve.
I'm going to have to go here. See what I told you? They disappear. The nodes disappear. After I exit It's amazing. I don't know how to keep them there. So here I had actually written stuff down, and they're gone now. You see, that's why I can't post the notes. I don't know if anybody knows how to fix that. You know? Okay, please. Oh, I use something else. Okay, yeah, that I could do it. Yeah. Anyway, so here we go. Right. We have a posterior for our weights. That posterior was like that, right? And this corresponded to our state of knowledge about the weights after we see the data. So what we do is we take a sample.
Take W.
Yes, take a sample of the W from this distribution, plug it into the generalized linear model. So from this, you take a sample, you plug it into the generalized linear model, and you plot it. That's where the red line comes from.
Why don't you just take a mean?
Because the mean will give me one line,
Yes.
and this is not better than any of these lines.
And what if you for each sample you have distribution for each x value.
For each x value, I do have a distribution, yes.
Yeah, why don't you take the distribution?
Because that distribution contains two kinds of uncertainties. It contains this uncertainty and the measurement noise. Now, what I want to do is visualize this uncertainty, which is just the epistemic uncertainty. So let's think about this. Let's say that what you really wanted to do in your life is take this model and connect it to another model, and then study something else that depends on the final model. Okay. So let's say that this is a measurement of a constitutive law, like Hooke's law or whatever, something that is an input to another thing. Okay. Of course, you want to filter out the noise that is it's just because of your measurement process. You want to filter it out, and you just want to keep your uncertainty about the model itself. Okay? That uncertainty is going to be there, and you better propagate it through whatever the other model is. Just to make it precise, imagine we have continuum mechanics here, is the model we're really interested in, and we're studying a new material that needs a new constitutive relation that we're going to find experimentally. So we do our experiments, but each experiment costs $1,000, so we can do 10. Okay? So we do 10 experiments, and there's a lot of noise, and we cannot really tell what is the constitutive relation. Okay? We cannot really tell. We could pick one, but nobody puts a gun on our face. So we say, let's quantify our uncertainty about this constitutive relation. But from that uncertainty, we want to filter out the noise. We don't care about the noise, because the noise is not there in the application. When the material asks for the constitutive relation, it doesn't use our measurement process, right? It just does whatever it does. So it's looking for that functional relationship. So that's what we're doing here. We're quantifying this uncertainty. So of course, if somebody tells you, tell me what you think at this x, tell me what you think y is at this x, you can say, it depends again, they may ask you, tell me what you think you will measure at that x. What is the y you will measure at that x? To talk about that, you should include the red lines and the noise. If somebody tells you, tell me what you think about x at that line, about y at that x, but filter out the noise, you will only talk about the red lines. Okay? But, and you will report again a Gaussian. But sometimes somebody tells you, tell me what you think about the whole function, because the whole function is needed to do something. So if you're doing continuum mechanics and this is a constitutive relation, you cannot sample it every time you need it. You need to sample the function and give that to your finite element solver and solve your problem. And then you need to sample another function, give that to the finite element solver and solve your problem. And this is the only way you can consistently propagate uncertainty through it. Maybe I'm going too slowly or too fast. I don't know. Probably both. Yes.
So, the first question, is there a way to reduce the noise, and is that in the scope of this class?
So, the question is there a way to reduce the noise? The answer is, it depends on the actual experiment you're doing, right? So, there's no magic way to reduce the noise. What you can do is you can estimate the noise and filter it out. That, yes, that's exactly what we're doing here. So here you see a result that has filtered out the noise, and you just see the remaining uncertainty. And you see that even though you have filtered out the noise, you can still not tell exactly what the model is. Yeah, but reducing the measurement noise itself, I mean, you have to make a better measurement instrument. There's no other way. Yes?
Given the current parameter information and the data that we have, can we at this stage determine like how many more samples will be required to reduce the epistemic uncertainty to a certain level?
Yeah, this is an excellent question. And the answer is yes. We can. How? It's another lecture. But yes, you can actually, this is the whole point that I'm going to try to make. Forget about the handout today, obviously. We'll do it next time. I'm still in the middle of the lecture, by the way. I have 20 more slides. So we'll continue on this on Tuesday. But this uncertainty, this epistemic uncertainty, should be used to design your experiments. So you should be asking, you can actually ask questions like, which measurement will reduce my epistemic uncertainty the most? You cannot talk about the whole uncertainty because some of it is irreducible, but for this one, you can talk about it. And you can construct, for example, a sequential experimental design procedure that selects the experiment about which you're maximally uncertain. You can, that would work. And that will reveal the underlying surface as fast in an optimal way, if you like. But you can take it even further. Instead of just trying to learn this function, you can look for specific attributes of that function. You can say, for example, well, I'm not really interested in in learning this function everywhere. I'm only interested in optimal properties. So, for example, I'm looking for the x's that will minimize that function. So you want to design experiments that will basically gradually discover that the minimum is somewhere there while filtering out the noise. This is also possible, and this epistemic uncertainty, again, it is the key to doing that. Or you may be interested in saying things like, you may be interested in finding a level state. So for example, if this is the structural response of a building, and if it exceeds a specific level, you're going to get damage to your building, then you'll have here like a limit state, and you're interested in the x's that will make your system exceed this limit state. So you want to collect data not everywhere where it is likely to exceed that limit state, basically. So that, again, if you want to come up with a sequential design of experiments that discovers that, epistemic uncertainty is the key. In general, epistemic uncertainty is the key for designing sequential experimental design procedures. So we better spend one more lecture on that. So it's the second time we teach the course, so we don't really know how fast we should go. Any other questions? Yes.
After you get a functional curves, what do the curves tell you?
Could you repeat that when I get?
Yeah, after you have got 100 red curve.
Yeah.
what do they tell you?
So here I see, when I see these curves, right, I see how confident or unconfident I should be about the predictions I make with these models, right? So if I see a lot of curves that are not really, on top of each other, this means that I should probably keep collecting more data. Or if I am if I am using this as an input to another model, the other model, it better not be very sensitive on that. Otherwise, I should include this uncertainty as well, right? This is the whole point of that.
Can you mathematically do something or just visually look at the curve?
Yeah, of course you can. I mean, you can only look at the curves visually when they are in 1D. But you can use them to propagate uncertainty through anything you want. This uncertainty, you can take it and use it as an input to other stuff. Yes? So we are going to correct that on Tuesday. We are slide 38. There are 20 more slides. So it will be extended. All right, but it's good to have this discussion because I'm probing the room for, the level that I should really present this. And I don't really know what you guys know, so it's good that you participate. It really helps a lot, okay? And the whole point of this class is to help you use this kind of stuff in your research. It's not for me to just say what I'm doing, right? So it's you should really bother me when I don't make sense. All right? Okay.